Hi, we're UltraSafe, and today I would like to discuss with you the development of our new product, Frequency Intelligent Navigation Device with Ultrasound, or for short, FINE-U. As a company, we researched the statistics for firefighter fatalities and realized that there would need to be an improvement in firefighter safety equipment. Current technologies, such as the past, implement a loud audible signal when a user is in distress to signal other users. We realized that in a case of a burning building, which is very loud and very extreme, the audible signal is not very ideal. Thus, we considered using ultrasound. Ultrasound works very similarly to the concept of radio frequency. However, unlike radio frequency, our ultrasound signal is devised to bounce and reflect off walls, thus giving a strong signal along accessible pathways. Ultimately, our FINE-U device will navigate a user along this accessible pathway to users in distress.
We began the design process by forming our team. Martin Chang was the team leader and was in charge of managing the project. Chau Diep was the materials expert and was also in charge of finances. Johan Fredriksson worked on research and development, establishing the testing protocols for the device. Nguyen was in charge of documentation for the project, working on team reports and posters. Chao Shen was in charge of developing coding logic and programming on the Arduino platform. Finally, Johnway Yih also worked on research and development, focusing on prototype fabrication. Assisting in the project was our mentor, Dr. Shiva Sharareh, who helped guide us in the design process.
After evaluating other designs on the market, we had to decide our own specifications for our device. Recognizing that firefighters carry over 80 pounds of equipment, we wanted to make our device lightweight and less than 2 pounds. Since firefighters are often crawling and burning buildings, we wanted to make the device hands-free for ease of use. In order to remove the need for a user to spin 360 degrees to determine which direction to go in, we wanted the receivers to be multi-directional. For a feedback method, we knew we had to overcome a loud environment with low visibility. As such, we settled on a visual display with LEDs attached to the helmet. Finally, a firefighter's tank of air typically only lasts 30 minutes, so we wanted to make sure the transmitter could function for at least an hour.
Our prototype features 2 components, a helmet mounted with the receivers and a transmitter device. In both cases, they feature ultrasonic transducers from Maxbotics, modeled MB1360s. These transducers run at 42 kilohertz, and although originally are for ranging applications, we have repurposed them for our navigation. Now, on the helmet are mounted the 3 receivers, mounted in a sort of T design, one in the front, one in the left, right, perpendicular to each other to give us a 3-way coverage of direction. Here, we're basically mounting our microprocessor, in this case an Arduino Uno, that processes the signal from the 3 receivers and then translate that into a direction for the user via the 5 LEDs in the front. These 5 LEDs give the user a general direction in terms of forward, left, and right, based on the 3 LEDs. In this case, the forward direction would be the 3 middle ones lighting green, and on the left and right would either be the left or right LED lighting green. Otherwise, they're red. Also, we took into account the fact that there isn't always necessarily a signal being broadcast, in which case the LEDs would be all yellow to tell the user that no signal has been detected or that the current signal that they are tracking has been lost. The transmitter features 1 transducer poking out of the top and has a switch on the side for turning it on and off. The transmitter you'll see on the inside uses an Arduino as well, also powered by a 9-volt battery. For future designs, we see that the transmitter would be more valuable if it could be activated not only manually via switch, but also through means of a biofeedback measure. For example, if the body temperature of the user was being monitored, or their blood oxygen level, heart rate, etc. If such things were to go into a dangerous stage of distress, the transmitter could automatically activate, thus warning other firefighters that a certain personnel is in danger.
So our initial coding logic is to basically take all the signals coming to the receivers and then calculating the direction based on the amplitude of the signals from each of the receivers. So we basically take the center signal as a y-axis and then take the difference of the left and right signal, and that's our x-axis, and then we take the arctangent of it to calculate the degree, and based on those degrees we can decide where the signal is coming from. Depending on the range of the angle, one of the 5 LEDs will light up. For example, if the angle is between 0 and 30, then the rightmost LED will light up. But the problem with that method is that the way we design our system, when we put the helmet on our head, it's really difficult to see which LED light up. So to fix this, we decided that if the signal is coming from the middle, then the front 3 LED will light up, and if it's coming from the side, then the side LEDs will light up.
In order to do our design, we realized we wanted to start with some kind of helmet as our foundation. Given our budget constraints, we decided to opt out for a basic safety hard hat helmet. We decided to build our device around the hard hat, however making sure that it was a device that could, in the future, be something that could be removed and easily integrated to other pieces of equipment, meaning that firefighters would not have to sacrifice their existing helmets, but could instead purchase the product and have it applied on top. In order to integrate the receivers, we decided to use a headband from a LED headband. Removing the LED flashlight, we then proceeded to attach the headband onto the helmet and mount each of our receivers on it individually. For the LEDs, since we realized we wanted both red and green LEDs, rather than mounting both colors, we decided to purchase bicolor LEDs and use them instead. Mounting the 5 LEDs, we first combined them to a common ground, which we then wired to the Arduino through the back. Each of the LEDs then used 2 different wires separately, which we routed around the helmet base, into the back, and into the digital ports of the Arduino. The 5 LEDs were then mounted on the front rim of the helmet using putty, and hot glue was used to keep everything together as well as to help insulate the wires to make sure that none of the signals could cross over and interfere with each other. We did take into account the fact that future designs would be prototyped and then later developed with fire-resistant materials. In this case, we chose to use PTFE and Nomex.
PTFE is also relatively cheap in the market, about $50 per kilogram. As for the headband, we decided to use Nomex wrapping because it's commonly used in firefighting industry due to its high flame resistance.
Testing is a vital part of product development, especially if the product is intended to save life, such as Find You. You first need to validate its capabilities, that it matches your design inputs. The testing will also provide feedback on what is working well or not. This will allow you to identify and restrict arising problems and enable relevant re-engineering. Our array of tests look like this. First, we have a range test, where we will see over what distances will our device be able to communicate. We will then test how the signal is attenuated by different types of barriers, such as paper, wood, smoke, or even elevated temperatures. Lastly, we will test Find You's ability to navigate. With only the signals from the LED display, one should successfully be able to navigate through the tease test lane or find the room. And this would be considered being real-life scenario testing.
From our range testing, we found that we could achieve a range of about 100 feet, which far exceeded our original expectations of only 70 feet given the transducers we were using. When we moved indoors, to about the same range resulted a little shorter, about 95 feet. When we applied this to going around a corner, we found that our range was limited down to 30 feet, which is a limitation of the chosen transducers, which have a beam width of only about a foot. In small-scale smoke tests, we found that the amplitude was not really attenuated much, but instead the width of the signal was. However, it is worth noting that the baseline here is a lot wider than our typical reading, given that this was performed in an enclosed container. When looking at a range of different amounts of smoke, we found that the average signal of the baseline was much greater. However, the maximum and minimum signals were about the same, with a slight drop-off with increasing smoke levels.
The market size for this device is for firefighters in general. Our prototype costs about $322, but if we were to mass produce, it's gonna cost about $143 for the transmitter set and about $188 for the receiver set, which is about $100 cheaper than the current pass system.
In the end, our Find You device was able to reach a range of 100 feet. Our goals of trying to achieve a weight of under 2 pounds was also achieved. Our transmitter weight was 0.2 pounds, while our receiver weighed 0.65 pounds. Our battery life for the transmitter was 13 hours, and our receiver lasted 2.5 hours.
Well, that is our project so far. Once again, we are ultra safe, and this was the Frequency Intelligent Navigation Device with Ultrasound, or Find You for short. Thank you for listening.